Two electrons interact through the exchange of a photon, and so such a process is described by quantum electrodynamics, and its Lagrangian is given by the sum of the Dirac-Lagrangian for the fermions, the Maxwell-Lagrangian for the vector boson, the photon in this case, and an interaction Lagrangian which couple the fermions with the boson. In the lowest order of perturbation theory, the amplitude for the scattering of two electrons is given by a sum of two Feynman diagrams, a direct and an exchange term. We only looked at the direct term and got its amplitude using Feynman rules for QED. Experimentally, we have access to the probability itself, which is the modulus square of the amplitude. And in principle, we need to sum both the direct and the exchange term. So we only looked at the modulus squared of the direct amplitude, and more precisely at the part which involves the spinors and the Dirac matrices. We then introduce the unpolarized cross-section, which is usually what we have access to experimentally, and which is proportional to the sum of the amplitude of probability, where we average the incoming spins and we take the sum over the outgoing spins. And because we have the product of two terms which are similar, we only looked at one of them, where we sum over the corresponding spins. And we see that the result involves traces of 2, 3, and 4 gamma matrices. So we argued that we have now all the tools to do a proper calculation of the fundamental electron-electron scattering using QED at the lowest order of perturbation theory. But how much work do we still need to produce in order to get a number which we can compare to experiment? Well, experimentalists give you cross-sections, and the cross-sections involve the prefactor, which we didn't take into account here. So we would have to include this prefactor. Also, we are summing over the spin, as we should, but we only took into account the direct term of the amplitude. In principle, we should have a sum of both the direct and the exchange term. It's not complicated to write down the exchange amplitude. However, what is complicated is the cross term when we calculate the probability, when we have the product of MD times ME star, for instance. Because at the end, this will involve traces up to 8 gamma matrices. Also, to complete our calculation, we should take the product of this term times this term, but we only looked at this one, and we should of course take into account the prefactors of the amplitudes and square them. So all this work is relatively cumbersome, and we will only do it in the simpler case where we have the annihilation of an electron with a positron giving a muon and an antimuon. And the reason why it's easier is because at the lowest order of perturbation theory, it only involves one Feynman diagram, and therefore we avoid the second term, the exchange term, and in particular the product of the amplitude between the direct and the exchange terms.